The time is nigh. You know what that means? I've been reading Game of Thrones, so I've been talking like all old school to people. They're like, shut up, Grismani. You sound like such a stupid dork. And that's true. That's what I am, born and bred. So I'm gonna give a few seconds for folks to come in. Did you see if anyone was in that room that we're waiting on? Okay, so that makes a reduced quantity for what I'm gonna ask. Oh, that's the wrong date.
Well, everybody's on.
Is that true? Wait, have these dates all been wrong? Oh, wow.
Yes.
So what, this was what, 21? Oh my gosh. Oh my gosh. There we go. All right, because there's the 29th. Yeah, that makes sense. Because we had a leap day. Okay. So we have a problem. Got a real problem today. Real problem. We got boundary value and got no person on boundary value. So how are we going to remedy this situation? What? Oh, it's empty. Empty right here. Wait, that's not the right one. Boundary value right here. Popcorn? What does that mean? No. There's some new math. Oh no, that's horrifying. No, because so remember what the goal of these things are. You know, I could sit up here and I could drone. And, you know, in some cases I do that. But you do yourself a huge disservice if you don't read the material before you come in. And I know sometimes life gets in the way, so on and so forth. So there's a little incentive to at least skim the book ahead of time. In addition to that, we do need to work on our ability to communicate. Because as you will see, and I'll ask about next week, okay, we have a code proposal that's going to be due. Now you're seeing all types of derivatives, and throughout this week and the next couple weeks, I'm going to give you examples of different things that you can code up on your computer. And you're gonna be like, oh, that was awesome. I really played with this experiment and, you know, it did X, Y, and Z. And as you get to the very end of the class, you're gonna have a final presentation inside of the classroom to everyone around you. And you need to be competent in talking about the techniques that you're using. So this is why we practice them, so that you can walk folks through a little bit of what you did, because communicating what you did is more important than the code. Now, why is that? 10 years ago, that wasn't true, right? Before the advent of AI, people who could write code and were just like hermit crabs who talked to no one were paid very lucratively. In the next 5 to 10 years, those jobs will all disappear. I guarantee it. Because as AI gets better and better at writing code, what's more important is your ability to interface with that code. Can you figure out whether it's right? Can you communicate that to your boss? Can you demonstrate that the thing does what you think it would do, right? Those are the important things. Now, it turns out those are actually really important in science too. But if you decide not to continue on, right, you don't want to be a faculty member, you don't want to be a research scientist, you just want to get out and make some dollars, okay? The more important job is not writing code. I promise you that. And if I had told you that 20 years ago, you would not have believed me. But you probably wouldn't have been alive either. So, or maybe not that alive, just a little baby. Okay? Mark this down, write it in your head. Grismani says 10 years, coding jobs will be extinct. Okay? So we're going to practice communication. We're going to practice presenting. Your names have been in here once. I see Isaac, Alfred, Zuri, Eduardo, Daniel, Andrew, Gonzalo went, Brandon went, and Katura. So I think that's everyone once, except for Jasmine. Is that correct? Mathematically? Yeah, that seems right. Let's see if Jasmine's on the line. No, just Katura. Okay, so that means that we have an opening. Who wants to go for their second time? Everyone will need to go a second time, if not a third. Isaac, you're ready? Wow, round of applause, round of applause. There we go, there we go. Okay, we're gonna dive into a bold new location. And if you were doing adaptive step size, and I wrote all that stuff on the board and you're still confused about it, that's perfectly okay. We can come back to that at the end of class today. But right now, what we're gonna do is we're gonna continue on with the idea of boundary value problems. Okay? All right. But I need to show you enough of these techniques that you have sort of a general idea of what to do before you propose to do something with the computer, right? If I just showed you how to use the computer and then I asked you to pick a topic, you'd be like, I don't fucking know what you can do, right? So we're going to see a lot of different types of problems. And then one of them is really going to spark your interest and be like, oh, that sounds cool. That makes sense? Okay, so let's go down to shooting method 8.6. And there's plenty of little techniques. As you go through here, I don't include anything on 8.5 in your reading or for this class. You're welcome to investigate them on your own. They basically change from RK4 to other types of techniques of forwarding the derivatives. So there's certain trade-offs. And when we talk about something like a simulation of molecules within a lattice structure, you might find that you want to use one type that is different than if you wanted to simulate a comet going around a star or a galaxy going around its supermassive black hole. Those all use slightly different techniques, and they all have pros and cons. And 8.5 is that section. So as you nail down on your topic, I may refer you to a specific section in there to try out a new technique. Does that make sense? But right now you can sort of avoid it. Let's go down to 8.6. Oh boy, that's deep. All right, the shooting method. Bang, bang, boundary value. Okay.
So we've been dealing with initial value problems, meaning that they're solving differential equations given initial values and variables. But now there are going to be boundary value problems. So we scroll down. So given the instance, the differential equation or the differential equation governing the height above the ground is defined by that second order ODE. So there's two ways you can solve this. So the second one, which is the one we're going to be talking about, is we're going to basically be giving it two conditions. One, the initial condition, and one ending condition. So you can specify the ball height, time, and x value of 0 at some later time t, and that would be the goal to satisfy these conditions. So problems of these kinds are called boundary value problems. They're somewhat harder to solve computationally than the initial value problems we had looked at previously, but a solution can be achieved by combining two techniques that we've seen. First one being the shooting method. The shooting method is a trial and error method that searches for the correct values of the initial conditions that match a given set of values. In effect, of turning the calculations back into the initial value problem. So if you consider the problem above, this problem where you're given the initial condition and not the velocity in the ball. All we know is that it lands at a later time.
Let's pause for a second here to reflect on what Isaac just said. So what he's saying, okay, is that I have a ball, which I don't actually have a ball. Okay, this is a ball, pink round ball. Okay, so we've done initial value problems. If I want to throw this to Alfred, at time 0, I have the location and the velocity. Now I need two initial conditions because the equation is a second order differential equation. So I need a differential equation for dx dt, which is v. So I need an initial v. And I need that second differential dv dt, which is the acceleration, and therefore I need to know the initial position, right? Okay. However, if I don't give you v, and I give you time at the beginning and time at the end, then there's only, usually, one velocity that connects those two. Does that make sense? So either I throw it really fast and it arrives quickly, or I throw it kind of slowly and it arrives more slowly, right? Or maybe it doesn't even make it, right? Because if I'm throwing it this way, maybe it falls and it hits the ground before it makes it down. Does that make sense? If I throw it really fast and up, right, makes it down. Make sense? Okay, so we're going to investigate that second type of problem where we're not given an initial velocity and the initial velocity is just going to fly out of it. Fly. Okay, go ahead.
Scrolling down a little bit, you can see that the shooting method involves one of the standard methods for solving differential equations, such as fourth order run cutter method, to calculate the value of the function. So then we use a root finding method, such as binary search, to find the value of this function that matches the given boundary.
Okay, so I'll pause you here. You don't know what a binary method is. You don't know what a root finding method is. That's okay. Okay, here's the process, and we're going to use it and we'll describe it more in detail. Okay. The shooting method most often can be shown with this. You throw the thing up, it comes back down. And you are going to make some decisions. Okay. In this example, you undershoot our target represented by the dot on the right on our first guess, trajectory 1. On the second guess, we overshoot 2. On the third, we're close, but still not here. So what you do is you look at where you were supposed to end up and where you ended up, and you either, you adjust one parameter or another until you go over and under and over and under. And each time you get closer to the midpoint. So you choose some level of accuracy, some width around 10, right? So let me actually do this online so that Katura can see. So you choose some width around 10 here and here, where you'll be satisfied that you got the answer right. If your first answer ends you at 8.5, you increase V. Okay? Then you overshoot it. So you decrease V, but not by as much, right? And then you increase it, but not by as much. And each time that you're doing that, you get closer and closer and closer. Does that make sense? Okay. And we're going to walk through the bisection method when we use it here. Do you want to walk us through this example? What's that? Okay.
So we're given the two first order ODEs for this. We'll be solving this using the run cutter method. And then from a binary search to find the value of the initial velocity that matches the boundary conditions. So here's the program. So here we're defining our variables: gravity, initial time, final time, run cutter steps, or the number of run cutter steps, and then the size of those steps. And then we have target for target accuracy for binary search.
Right. So what does that mean? Target accuracy. Let's go back to that picture that I just drew here. When was I talking about the target accuracy? Yeah. Right. Well, so actually what we're worried about here is how far for the target accuracy, we're worried about how close are we going to get to the target. So we need to create some width around it in which we say, okay, it's within this is fine. Right? That's the target accuracy. And the number of steps that we take along the way is just going to be fixed. We're just going to say we're going to go from time 0 to 10, and we're going to take 1,000 steps, regardless of how fast we go. Now, that's maybe not always wise, but we'll talk about those differences later. Okay, let's continue talking about the code. Is this different from what we've seen before? So the only difference here is that they disgustingly have put X and Y. Right? And if you just read Y for what we normally think it is, you'd think that that was a coordinate in this direction. That's very annoying, right? Because you're throwing a ball upwards. So in fact, we're going to remove those things from our mind. X here is, of course, the position, and Y, by definition, is the velocity. Good. Okay. So if you go to do this example, which I encourage, what's the first thing you're going to do? Change the Y to a V, correct. Okay. And make sure that we do it everywhere. Okay, so this would be f of x would be y, f of y would be g. Does this one make sense? What's that line mean? What? I heard it. Yeah, what is that? Is that it's the acceleration. Exactly right, right? Okay, that's the acceleration. And then we simply return the velocity and the acceleration, and we do our RK4 as normal. So here's your array. There's the RK4 as normal, right? And then you have this thing that returns R0. What the heck is R0? Yeah, it's your initial position, right? So let's look at it here. You have a function called height. Given an initial velocity, okay, that initial velocity goes in here, bang. Initial position is 0. Then we let it run for however long we want to run it. And then we return R0. Now, what is R0 here? The what? The x position. At the beginning? At the very end. Do you see? So even though it says R0 and we might think in our mind, oh, that's still the initial position, all of this stuff has happened in between them, right? Exactly. That's the final position. So this little definition that we create, we hand it something. We say, here's your initial velocity, or a guess at your initial velocity. And it spits out the final position based on that initial velocity. So now we can use this little module and we can just go up and down in velocity space. We just keep trying them out till we get it right. Does that make sense? Intellectually, how we're thinking about this? Okay. And then this is the binary search that we're going to talk about in detail. You want to walk us through this? Does this make sense to you, or you want me to try? Okay. All right. Here's the velocity 1. Okay. Here's velocity 2. Are they similar? Very, very different, right? Okay, so one's very small, one's very large. And then we have some initial heights. Here's height 1, height 2. Right? V1, V2. Okay. So this thing here says while absolute value of h2 minus h1 is greater than the target velocity, sorry, the target for our code, remember this was 10 to the minus 10 from the very beginning. So that's that width, right? We say, as long as that difference is larger than 10 to the minus 10, run all of these things. Okay. So the first thing that the code does is it takes the average of the two velocities. Okay, I have a velocity over here that's really slow and a velocity over here that's way too fast. And it picks the one in the middle. And it says, what is the height based on that? Here, let me draw this because this can be really important. Okay. All right. Okay, ready? So here is the velocity space. This is V. Okay, here's 0.1, and here's 100 or whatever, 1,000. Okay. So the first one they try is here. And that's like 500, right? Okay. And you get some answer because we've done RK4 a bunch of times, and it spits out what? The final position, right? So here it gives us an answer of a final position, X final, right? Okay. So now this is where it gets really fun. If H1, so H1 was the velocity over here. So sorry, this is, let's call this, let me use the same letters. So this will be H1, This will be H2. And this will be HP, just to use the same letters then. Okay, so this is VP. This is V1, and this is V2. You see that? So you put in initial velocity, they give you out a height. Initial velocity, they give you a height. Initial velocity, they give you height. Okay. So now if HP times H1 is greater than 0, what does that mean? Yeah, let's have a look at what these might look like. Okay. This is a little coordinate system. You throw the ball up, it comes back down. Where is H1? Well, remember that it takes 10 seconds. If you don't give it a lot of space, or if you don't give it a lot of time, I should say, where does it end up? Does it actually hit the ground? No, because there's no ground in our simulation. Nothing told it to stop falling. So it probably ends up super negative, right? Okay, so H, let me draw this better. Sorry if you can't see this online. So H1 is probably down here, right? And H2 is where? It's, yeah, it didn't come back down. It's fucking 1,000, right? So H2 is probably way up here. And more than likely, HP is in between them. We would expect that, right? So let's imagine for 500 that HP is right here. Okay, now let's look at the product. H1 times HP is what? Is it? In the way that I drew it. Because it's negative, right? Okay. Now, defer. Let's go, baby. Okay, so this is not true, so we're going to use else. So what we're going to say here is V2, this one here, we're going to rename VP V2. And we're going to ignore this forever. Too big. Okay. And we're going to say that this is no longer HP, this is going to be H2, and we're going to ignore this forever. Okay, so now we're only going to look in here to here. Right? We excluded all of those results. You see? So let's do it again. Now I take the halfway mark. Right? Okay, where do I want the ball to end up after 10 seconds? At the initial position, which was 0. So that's why I'm choosing plus or negative, right? Because if it's above this, I need to make it go faster, right? If this is positive, I need to speed it up, right? If it's below it, I need to slow it down. Does it make sense? Okay. So now we picked HP, which was there. We calculate, here's VP, and that'll be like 250 now. And HP is like down here. And look, we still have the negative number, so we slow it down again, right? And then we accidentally slow it down too much, and you increase it again. Does that make sense? Okay.
Those steps we're doing it manually, or is it gonna be doing it like looping itself until it gets to that number?
Yeah, so this is the bisection method. And if you're curious about this, this method comes from a section in, I think it's chapter 7. And this is a standard method. So you pick one value over here and one value here, usually very far away from where you think it'll be. And you just let it go back and forth until it finds exactly the right answer. Right? There's other methods to use as well, but bisection for us is clean, right? It's only like 8 lines and it does what we need it to do. And then at the very end, we take V1 and V2, we take the average, and that gives us a very close answer. Does that make sense? Okay.
Is the B in the bottom gonna mess up when we change the Y to a B on top?
Yeah, so let's be careful here. Let's call it a, Vx, right? In this part here. In this part here, call it X and Vx, right? And that's always better anyway. Whatever this was called in your code, V2X or something, whatever you want to call it, VXX. I don't mind as long as it's consistent. Okay. We could talk about the relaxation method. But do you want to try that first? Yeah, the example. So this is example 8.6. It's going to be similar to a pair exercise that I believe I have. Wait. No, here we are. I think it's 8.8. Just double check. I'm doing what I think I'm doing today. Oh God. No, 8.8 is a previous technique. Oh God. That's fun too, actually. No, let's not do that. Let's do. Oh God, sorry, folks. I think we should just try 8.4. I mean, I know that the code's there. So what I would really recommend is you can do start with that here, just this part at the bottom, and try to code it up. Make the changes that we think we're gonna make, right? And see how they work. Walk through this and put your comments in. And I think if we spend like 20 or 30 minutes just on this one, it'll prepare us to talk about the relaxation method, which is the one that we're going to use for the problem today. We may not finish that problem today, but it's more important that you see both of these techniques sort of back to back. So there's not a problem on this, but you'll see it later on. So let's break up. We'll take a quick break from me chatting and we'll just get to coding, get the brains working. Resume recording. Okay, so we are going to learn another technique called the relaxation method, and it's not as fun as it sounds. Okay. So even though, wait, where'd it go? Even though, we just learned the shooting method. Did the shooting method make sense? Like what we were doing, why it's called shooting? So you pick, yeah. Yeah. So let's go back to the picture, right? And this picture is helpful. Basically what I'm doing And here's the analogy, right? Maybe I love analogies normally, so I'm a little disappointed in myself that I didn't start here, okay? We got a pew-pew, okay? I know you're not supposed to bring these to school, but okay, we got one. And we're going to aim it, right? We're going to aim it straight up. And somehow this pew-pew can adjust the amount of whatever gunpowder or whatever, okay? So we fire a bunch of bullets and they go up and they come back down. Okay. The target is here, okay? So this is where we want it to end up at the end of 10 seconds. The question is, how big are you willing to accept? So if your target is plus minus 2, then you would accept anything between 6 and 12. The target that you wrote down, I think, was 10 to the minus 10. So that's like really, really small, right? You got to get exactly on 0, right? So, sorry, in height. At the end of 10 seconds, right? This target is this way, right? So maybe I'm confusing things here. For velocity 1, it's not going fast enough, and at 10 seconds, it's below the graph. For velocity 2, it's going too fast and it's above the graph. And target gets it too low here on 3, so we'd have to shoot with more velocity to get it above again. You see that? Okay. So that's one way of doing the shooting method. Now let's talk about the relaxation. Okay? Sorry. I'll not do that one. So this method involves defining a shape for the entire solution that fits the boundary condition, and then letting it propagate from the boundaries to the middle. Okay? So it just changes the shape over and over and over again while keeping the boundaries fixed. So we keep the edges fixed and we fix everything in between until it's smooth, according to whatever formula it describes for that region. So if you imagine you have some charge distribution, let's say I have a positive charge in the middle. And at the edges of my box, my three-dimensional box, there's no charge. Or there's no electric field or something. Okay, charge in the middle, electric field is 0 everywhere else. So that must mean that in the middle, there's a big spike, and then it decays off to the edges, right? So I might have some boundary conditions on the edges, and then maybe I have to find how to smoothly connect them. Boom. And that's what I'm going to have my computer do. Or maybe I have an empty box, completely empty, and one edge has voltage, and the other 3 edges don't have voltage. So then the voltage is going to sort of diffuse into the box, but it has to go to 0 at all of the edges. And I'll just let the computer figure that out, right? And we'll talk about how we do that in the relaxation technique. But that's the basic idea, okay? So we're going to use that for partial differential equations. So we won't see that today, but we will see eigenvalues. You guys know what eigenvalues are? What's that? Solutions to functions. They're special solutions to functions. In particular, we use them a lot in quantum mechanics. So who's taking quantum mechanics? Who's taking modern physics? Or who is taking modern physics? Right? Okay. You all finished it, or are you taking it? You all finished. So you've seen psi before. So you're big fans of psi. It makes perfect sense. You're ready to give a lecture on quantum mechanics. Yeah, that's true. Okay, I get it. Took me a while to compute. Okay, so over here we have some funny looking symbols. This is our h bar. That's a constant. That's the mass of the particle. And here you have something which is the double derivative of psi. What does that mean? What? Kinetic energy, yes. So here you have something like psi, which is essentially where we think the function might be, or the particle might be, according to this function. And the double derivative with respect to space gives you what is essentially the kinematic energy, or the kinetic energy. And over here, you see your familiar symbols. That's your potential energy. And that's our good friend, the energy, the total energy of the system. Okay. I'm not going to talk you through too much of how eigenvalue problems work, but I'm going to show you how we can solve them using a computer. because essentially we're going to consider a particle in a square well. Have you seen this problem before? Okay, so this is a real life problem. Even though it seems sort of absurd, I'll show you how we use it in practice. You have some space. Okay, and that's infinitely tall. And I'm really good at drawing infinities on the board, so that's infinitely tall, and you all believe me, right? Okay, and down here, V is 0. Okay, and up there, V is infinity. Okay, right? So for a given energy, given finite energy, the particle cannot exist over here, right? Because if I go back to my example, sorry, my equation, here, this is infinite, and here, this is finite, and I'll never get enough kinetic energy to get them to cancel. Okay? So it simply cannot exist in here or in here. So that means that if this is the distance in x going this direction, okay, this would be L, and this would be x equals 0, right? That means that psi, this function at 0 equals what? 0. It has to be 0 because I can't have some discontinuous function like this, right? That goes through a boundary and then okay, that's just not physical. So there's no probability of finding it in the wall. So the probability of finding it is only between these two boundary locations. Now, where you're most likely to find it, I don't know yet. That's going to depend on the energy you give it. Okay. So maybe you'll find it right here, mostly in the middle. Maybe you'll find 2 bumps of it. We're going to find out. Okay. What about over here? Psi at L. 0. Good, for the same reason. Okay. Those are our boundary conditions. And you will see this in many, many different contexts. If I have a rod and I heat up one side and leave the other in a cold bath, and I want to know how the temperature is distributed from one end to the other, it's not too dissimilar from this. The only thing that's changing is the equation we use to describe it. So even though we're going to do quantum mechanics today, you don't need to know the quantum mechanics in order to do it, right? We're going to train the computer to solve the problem just like we would with any other force, right? And we're going to make some small modifications to this technique, okay? Okay. So here's our potential, okay? And if you look back over here, we want to solve for this thing psi, right? And if I look at it very carefully, I do see some fun stuff, right? Here on this side, I have a double derivative of psi, and here I have it by itself. So what order differential equation is this? Second order. Has to be, right? Is it partial? Or is it ordinary? It's ordinary. Why? Good. And I can also tell that just from the fact there's D's up there. I might have written this wrong if I wrote it on the board, but I'm pretty sure they wrote it right in the textbook, right? Okay. If you see a partial up there, that's how you know it's a partial differential equation. If it's a D, it's ordinary, usually, right? Okay. Good. So I can break it apart into 2 things. I can break it apart into d psi dx, and we're going to call it phi. That would be like the velocity of psi. And then here, d phi dx is going to be that stuff that we had before. Okay? And the basic thing that we're going to do here is we're going to solve the second order differential equation, and we're going to use the shooting method. What? What are you talking about, Krismani? Okay. We need 2 initial conditions. We know the value of psi is 0 at x. We know that the value of psi is 0 at L. but we don't know about the second derivative or the derivative at 0, right? So we have to guess an initial value and then calculate the solution. Okay. Let's see if I can go down to the example. Here it is. Okay. Here's the solution to the Schrodinger equation in a well. Are these right? Does it look right? Why not? Yeah, it doesn't go to 0 where we need it to. So this needs to come down faster. So these are some initial guesses, right? So the technique that we're going to use here, we can start with this thing, right? And have some of the constants that we had, H bar, M, E, L, N, how big our steps are, etc. Here's the potential function. Stupid, right? 0. So, you know, you don't need to write this. You can write 0. But generally speaking, you might want that for a different potential function, not the one we're about to do. And here's our new Runge-Kutta, essentially. So I have psi and phi. Remember, those are what were our x's and our y's. And here's psi, that's phi. And here's phi, and that's that stuff. Okay. And then you return both of them. Okay. So how do we calculate the wave function for a particular energy? Well, we need to give it some initial guesses. And then we need to run it. This is our RK4. And then we need to return it. Right? So that's not that different from the one we just did, where we gave it an initial velocity, right? We had it import it, we ran it through, and then we had it return what its final velocity was. And this is very similar. We're going to start at one end. We're going to shoot off and try to get it to go back down to 0 over here. Okay? You can use the secant method, or you can use the bisection method. I don't care. Here you'll need 2 initial conditions, right? So you have the energy of 0 and the energy 2 of E. So you know that the first energy that you're trying to find is between 0 and E. Why do we need an energy? Well, that's the piece up here. That's this piece, right? It's trying to find a location where this piece gives us a solution that goes to 0 at the edge. Does that make sense? Okay. Okay, so we can start with this one here. And you can do the secant method, which is another form of finding roots. Or, and I encourage you to do this, take the bisection method that you just used and convert it for this example. Now, I will encourage you to keep V0 written like this, even though it's stupid, okay? And the reason for that is that we will be able to then just change this potential function and everything else will work inside of a square well. Now, you can go about changing the shapes of the well by changing the potential function. So you could find Schrodinger's equation by changing none of this stuff below and only changing this potential function, right? Let's say you want to figure out where the first energy level is inside of a hydrogen atom. You simply have to put the potential of the hydrogen atom right here. Does that make sense? Now, you won't know that off the top of your head, but I'll show you how to do that. Okay? You okay? Yeah, okay. Just look blown away for a second, so I want to make sure everything's okay. Okay, so let's start with this problem, because we are going to head towards this idea of a quantum oscillator, where the potential looks like this, a parabola. Okay? So let's try it first for the easy one. Reasonable? Okay. And let me know if you need me to be up or down here. Okay. Questions, comments, concerns?